Okay, I'm going to start the class, okay?
Yes, sir.
Yeah. If there is any lag in the internet or in the video or audio, you just inform me earlier, okay? So that I will get to know because I'm connected through my phone hotspot. So is the presentation visible?
Yes, sir.
So you could see week 6, right? Week 6 topic. Okay. So in the last, good evening once again. Good evening, everyone. So in the last class, last two classes, we have been seeing about like shear force diagrams and the bending moment diagrams in beams and also as point loads. Okay. So again, we will work out some two problems in bending moment diagrams and shear force diagrams, and then we will be moving to the topic of bending and shear stresses in beams. Okay. So is my voice audible?
Yes, sir.
Okay. So this is a small problem which is as shown here. Okay. So can you work out and come up with the answer of the absolute maximum bending moment for this shear force diagram of a beam? Let us say this as point A, this as point B, this as point C, this as point D, and this as point E. Okay. So if there is any lag in my audio or video, you just inform me earlier. Okay. So can you are you working out this problem?
Yes, sir.
Okay. So how to find the bending moment at B? Any idea?
5P into A.
Yeah, it is 5p into A. So what is the concept which you have used in this in solving this problem?
dm by dx equal to q. QV.
Yeah, dm by dx is equals to b, which means like I'm actually calculating the area of the shear force diagram, and I'm actually writing difference of that is equals to the shear force diagram. Okay, area of the shear force diagram, which is like difference between moment at point B minus moment at point A equals to minus 5p into A. Is that right?
Yes, sir.
Yeah. So what is the bending moment at point A? You can assume, since they haven't given any information, you can assume this as a simply supported beam from A to E. Okay. So the bending moment at A will be 0. So you will be getting MB equals to minus 5 PA. Okay. So what is the bending moment at C then?
2P.
Yeah, it will be 2P, I think so. MC minus MB equals to 7P.
2AP. 2AP, sorry.
Okay. 7P into A. So MC is the unknown and MB is actually minus 5PA, which is equals to 7P into A. So MC is equals to 2PA. Then what about MD value? Moment at D?
Minus 2p.
Minus 2PA. Okay, let us see. So MD minus MC is equals to 2P into A. So MD is the unknown here. Minus 2PA is equals to, sorry, here minus 2PA should be there. So minus 2P into A. So which gives MD equals to 0. Is it correct?
No, sir.
Okay.
It should be 4 p.m. also.
Correct, sir.
No, actually here the area is in the negative region, right?
पर सर 2p into 2p तो minus 4p होगा ना.
I mean, see, 1 minute.
2p into 2a.
See, actually MD minus MC is equals to minus 2P into A. Okay, and the value of MC is I'm getting from here, right? Which is positive value of 2PA.
No, sir. CD length is 2n also.
Oh, sorry. Yeah. Yes. So 2P into 2A. Yeah. So which is minus 4P into A. So MD is actually nothing but minus 2PA. Yeah. And what will be the moment at E? It is trivial, right? It is equals to 0. So what will be the value of the absolute maximum bending moment?
5 p.m.
Yeah, it will be 5 PA. So answer is 5 PA. Okay. So next proceed to the next problem, which is based on the concept of compound beams. Okay. So here again we will be seeing about the shear force and bending moment diagram of a compound beam. Okay. So the problem is you are having a
Sir,
cantilever. Yes.
sir, if in the previous problem the absolute term अगर नहीं लिखा रहता तो तब भी the answer will be 5p है ना.
Yes. See,
Because we
if
have not mentioned the
here they have asked only
direct.
the absolute maximum bending moment, right? So we are writing it as 5 PA.
If absolute was not written in the question, then
Yes.
it will be.
Yeah, then it will be the maximum bending moment and we have to write it with the sign. That's it. Minus 5 PA like that we have to write.
Okay.
So in the options, if it has been mentioned like minus 5 PA is in the option, then you can go for that. Okay.
Okay, sir.
Yeah. So this is about the compound beam. Okay. So here we are having a beam like this, which is simply supported at this end, and you are having a fixed end at the other end. Okay. So here actually at the midpoint, okay, it is actually hinged. So you are having two beams which is hinged at point B. Is this clear or not?
Yes, sir.
Yeah. And you have a loading at point, let's say this is D, okay, which is of 10 kilonewtons. This is 10 kilonewtons, okay. And the length from here is 1 meter, and the length from here is 3 meters, and the length of this is 4 meters. So, can you find the reactions at A and C?
Yes, sir.
Yeah. So, I will tell you how to find the reactions at A and C, okay? So, in order to see, this is a compound beam. Here you are having one beam from A to B, and at point B there is a hinge, okay? And from B to C it is another beam, okay? So, in order to find out the reactions, what will be the reactions actually when you are drawing this? Okay, I am drawing a separate thing here. You will be having a reaction here, right? As well as a moment reaction, yes? Which is equals to MA. So I am taking this as point B, okay? And I am actually separating these two beams, okay, only for finding out the reactions. So I am drawing the second beam here, okay, and here you will be having one reaction, right? Which is RC. And this is again point B. And here you are having 10 kilonewtons. So I have separated here. Now can you find the reaction of R? I mean, now can you find the value of RC, RA, and MA?
RC is 2.5, RA is 7.5,
Okay, and the value of MA is
30.
4
yeah
into
30. Yes. So how we actually arrived at reactions? Actually, first for this compound beams, we have to separate these two beams into its individual constituents. Okay, and after that, uh, whether can I solve the left hand side beam or the right hand side beam very easily in order to find the reaction RC. Like if I separate it out here, I will be getting a reaction. Okay, and equal and opposite reaction I will be getting here since point B is hinged and since there is no external force, the internal force should be balanced with each other. So that only I am drawing an upward reaction here as well as a downward reaction for this member AB. Is it clear what I am doing?
Yes, sir.
Okay. So after doing this, can I find RB value based on like which side I have to choose? Either left hand side I have to choose or the right hand side beam I have to choose for finding out the reactions.
Right hand side.
Right.
Yeah, right hand side. Yeah. So what I will do is like this is 1 mm, this is 3 mm. So if you draw, I mean, from the summation of F is equals to 0, you will be getting 10 kilonewtons is equals to RB plus RC, right? And if I take the moment value about B, okay, summation of moment about B equals to 0, which means RC into 4, which is equals to 10 into 1. Is it correct or not?
Yes, sir.
Yeah. So what is the value of RC? It will be 10 by 4, which is equals to 2.5 kilonewtons. And the direction is upwards only, as we have taken. Okay. So from this, I can find the value of RB, which is nothing but 7.5 kilonewtons in the upward direction. Okay. So why I'm putting for the member AB the shear force at RB as downward for this member AB, because like this point at B is actually balanced, okay, or there are no external forces acting on this hinge. So any reactions which is acting on this point B will be balanced by uh, the two beams, okay. So when I am taking the left hand side beam, here I am drawing the left hand side beam separately. Okay. So this is 7.5 kilonewtons. Okay, and this is RA, and I am having some moment. Okay. So the length is like 4 meters. So what will be the total moment value? It will be like 7.5 into 4, right? Which is actually, and it is actually acting in this direction, MA, where MA equals to 7.5 into 4, which is equals to 30 kilonewtons meter. Okay, and the value of RA will be equal to 7.5 kilonewton. Okay, so for this, can you draw the shear force diagram? And what will be the variation of shear force diagram from A to B or from B to D and D to C? And whether it's positive or negative?
So positive 7.5 kilonewton.
Yeah, it is positive and it is 7.5 since like the shear force is causing a moment in the clockwise direction, okay? So it will be positive. So it is 7.5 kilonewtons. Up to what value it will be 7.5?
Sir, B.
B or some other point? Since when you are looking at the whole beam, right? Now you are actually looking at the whole beam for drawing the shear force diagram. For example, you
Right.
have
D. D.
Positive, sir.
D.
D, yes. So up to D, I will be having this 7.5. And at D, what is the shear force? 10 kilonewton is acting downwards, right? So when I'm taking a cross section here, so it is causing a moment in the anti-clockwise direction. So it is actually negative. So I'm drawing a 10 kilonewton force here. And then RC is actually 2.5. So in the negative direction, it will be 2.5. So it is negative. And this is point D, this is point C. Is it clear? Is it clear to everyone?
Yes, sir.
Yeah. Then can you draw the bending moment diagram? Or can you draw from this shear force diagram itself and say what will be the value of the bending moment diagram at point A?
-30.
Minus 30, yes. Since it is left anti-clockwise, okay? So we are writing minus 30. And then what will be the variation of the bending moment from A to D? Whether it will be a parabola or a straight line or a like straight line with, yeah,
Straight line, sir.
yes, straight line. And what will up to what I have to draw the straight line? Like, can you say what will be the bending moment at point D?
पॉइंट बी पे तो जीरो होगा सर.
Yes, point B. At point B, the bending moment is 0. So we will draw at point B, which is exactly at its center. Okay, the bending moment is 0 because it is a hinge. So you won't be having any bending moment. Okay. So at point D, what is the bending moment value? Let's say this is point D. Okay. What is the bending moment value at point D?
7.5.
1.5.
Yes, it is
Kilonewton.
7.5. Actually, RC into 3 will give you the bending moment value at point D. Okay. So 2.5 into 3 will be 7.5. And whether it is positive or negative?
पॉजिटिव है सर.
Yes, positive. So this is 7.5. Okay. And then at point C, it turns to 0. Okay. So, for example, in any other beam, if you are having the bending moment, for example, in the bending moment diagram, if there is a change in the bending moment, for example, here it is negative and here it is positive, right? What you will term this point B?
Point of contraflexion.
Point of control.
Yes, point of contraflexion. Point of contraflexion is nothing but the point at which the bending moment changes sign. Okay? Yeah. So here we can say B is the point of contraflexion. Okay. So up to this it is clear, right? So I am going to stop the shear force diagram and the bending moment diagram topic with this problem. Okay.
Sir,
Yes.
point of inflection means, sir.
Point of inflection means like I think like it's similar to, no, I actually don't. I will refer and I will say. Okay.
Okay, sir.
Yeah. If somebody knows also, they can help him.
What is the question, sir?
He's asking about what is meant by the point of inflection.
Okay, sir.
Yeah. Maybe in the next class I will let you know. Okay. Yes.
Oh, okay, sir.
Yeah. So in today's class we will be seeing about the bending moment, bending stress, and the shear stresses in beams. Okay. So directly I am going to write the bending equation. Okay. Can anyone say what is the bending equation?
M by A equal to sigma by m.
Yes.
T.
M by I equals to sigma by y equals to E by R.
Equal.
Yes. So here M is the bending moment. Okay. I is the second moment of inertia. Okay. Or second moment of area or moment of inertia. Okay. Here I will write moment of inertia. MOI. Okay. I am writing in short form. And then sigma here is the bending stress. Okay. And y is the distance from the neutral axis. Distance of a fiber from the neutral axis. What is the neutral axis?
Where bending moment is zero.
Zero.
To the center of
Yes.
gravity. Wide.
Yes, where the bending moment is zero and where the bending stress is actually zero, not the bending moment is zero. Or else we can say like that also. Means like even though the we can say like here for example in the neutral axis the length of the axis doesn't change, okay, or the length of the surface does not change even after the loading. Okay, for example I have a bar like this. Okay, with a cross sectional area of b into l, maybe we can say this as a rectangular, it has a rectangular cross section. Okay, so if I'm subjecting this to a constant bending moment, okay, and after bending I will be having a shape like this, right? It here for this loading the top fiber actually contracts whereas the bottom fiber elongates. Okay, so somewhere between these two you will be having a surface where the length of the surface before and after bending is actually the same. Okay, so that surface you term it as the neutral surface, and actually when you are seeing the cross section from this side, okay, so I've told you this is a rectangular cross section, so we can take this as like width b, okay, and depth d. Okay, so you will be having this as the neutral axis. Okay, for every cross section you will be having this neutral axis. Okay, and E is the Young's modulus and R is the radius of curvature. This radius of curvature, this is the radius of curvature. Okay, somewhere about a center it is actually curved. Okay, so that radius is termed as the radius of curvature. So with this bending moment equation, so we can say like whether can you say whether neutral axis coincides with the centroidal axis of the plane of cross section every time, or whether it actually changes, whether the neutral axis whether it can lie in between the fibers or whether it can lie outside the fiber, something like that.
Sometimes coincide.
Sometimes coincides and sometimes it doesn't coincide. So can you say when it coincides with the centroidal axis?
It depends upon the moment of area.
No.
For symmetrical shapes, it will coincide.
Section of the beams.
Yes, for symmetrical things, yeah, we can say the neutral axis coincides with the centroidal axis. But for even for a neutral cross section, for example, here we are actually saying about pure bending, right? So what happens if I have what to say an axial load also? For example, I am having an axial load as well as a bending moment. During that time, can I say whether the neutral axis coincides with the centroidal axis? Neutral axis is
No.
actually where the bending stress is actually zero. Okay,
Yes,
BS
sir,
is,
it will coincide.
see, for pure bending we can say the neutral axis coincides with the central axis, whereas for the what to say for a beam which is subjected to an axial load as well as a pure bending moment, can we say whether the neutral axis coincides with the central axis?
Lost.
No.
No,
Yes,
that's the challenge.
yes, it won't coincide because, like for example, let us take this case itself, okay? And maybe what we can do is like we can take a rectangular bar, okay? And I'm subjecting this rectangular bar to an eccentric. This is the uh, longitudinal axis of this member. Okay, so actually subjecting this to an eccentric axial load. Okay, let this distance be d by 6 or something. Okay, or y you can say, or we can take this as e. Okay, so due to this, how can I actually represent this same system?
PD by 6 moment.
Yes, PD by 6 as the moment and P as the axial load, right? So I can replace this by PD by 6 as the moment and P as the axial load. So during this, what happens? When you are considering only the axial load at any cross section, what you will be getting only tensile force, right? Which is equals to P by, for example, if we are taking like this cross section as B and D, what you will be getting as the axial stress, it will be like P by BD, right? Due to axial load, the axial stress will be P by BD. And what will be the bending stress? Sigma, which is equals to
M by I.
yeah my by I. Here, what will be m, which is pd by
PD.
6. Yes, and what will be the value of y? Y is the distance of the fiber from the neutral axis. Okay, so here we can assume like for pure bending the neutral axis is corresponding to the centroidal axis, and then we are taking the uh, y as d by 2. Okay, sorry, I have written it here. So it will be d by 2 divided by what will be the I value for a rectangular cross section?
PD cube by 12.
Yes, BDQ by 12. So ultimately, what will be the bending stress value, maximum bending stress value?
P by B.
Yeah. See, for example, like d by 2, if I am writing, I can write it as this 6 to 12 gets cancelled. Okay. So it will be P by BD. Correct or not?
Yes.
Okay. So this sigma max is equals to P by D. For which fiber it will be positive and for which fiber it will be negative. Or if you draw the variation of the bending stress, can you draw the variation of the bending stress here for this cross section? Like for example, at the top fiber, whether it will be positive or negative.
Negative.
Negative, yes. So I'm drawing it like this, okay? Since it's a compressive load, I am drawing it like this, okay? The variation. So this is the P by BD and here also P by BD. And if you draw the axial loading, it will be something like this. Okay? So when there are three conditions actually. When sigma A is greater than 0, I mean sigma A is greater than sigma B or the sigma B max. Okay? What will happen for this condition? For this condition, for example, if sigma A is greater than sigma B max, what will happen?
We design the beam based on the axial stress.
Yes, see, actually, when I'm drawing this, you can actually say like, for example, sigma. here it is compressive, right? At the top it is compressive here, whereas here it is tensile. So when I am drawing this, the net effect would be tensile. Okay, I am actually combining sigma A plus sigma B max. Okay, so at the top layer it will be tensile because sigma A is greater than sigma B max, and at the bottom layer it will be again tensile. So the variation will be something like this. The net effect due to axial stress as well as bending stress. Is it correct what I have drawn? When sigma A is actually greater than sigma B max? See, actually sigma B A is actually fully of tensile. Okay, so if I draw a particular cross section, it will be like this: internal resisting force, right? Since I am having force like this, so I have drawn the resisting force or the resisting stress like this. Okay, this is sigma A, and what the variation which we have drawn is like compressive and tensile. Okay, so it will be something like this. Okay, so this will be in this direction and this will be in this direction. So what I am saying, this is sigma B max. So what I am saying is like for the particular condition of sigma A greater than sigma B max, my net effect is like this. Is it correct or not? Whether what I have drawn is correct or not? Here it will be sigma A minus sigma B max. Okay. With, for example, let us take the axial stress value as 50 megapascals. Okay, and the maximum bending moment as 30 megapascal. Okay. So here, since you are having compressive stress, what value you will be having? Because this is tensile and this is compressive, right? Here, the top layer is in compressive stress, whereas the bottom fiber is in the tensile stress. So the net value or the net stress at the top fiber will be 50 minus 30, which is equals to 20, whereas at the bottom it will be 50 plus 30, which is equals to 80, which is tensile here, and also here 20 megapascal tensile. So only I have drawn the variation like this. Okay, yeah. Yes.
Yes, sir.
Yeah. So at the neutral axis you will be getting only sigma A because sigma B equals to 0. This variation why I am drawing like this you are getting, right? So during this, where the neutral axis will be located? Neutral axis will be located outside here, somewhere here. Okay, here only you are getting the total stress as 0. Okay, neutral axis will be located here, outside. And if sigma A is less than sigma B max, then you will have the neutral axis somewhere in between the cross section. Okay, or somewhere in between the fibers. You are getting what I am saying, or should I have to work out some problem? Then you can understand what it is.
Sir, I'm not getting that neutral axis concept for
Okay.
this.
Okay, then I will explain this using a problem. Okay. See, neutral axis is where the stress value is actually 0. Okay. For example, in pure bending, the neutral axis is actually the where the bending stress is 0. Whereas for any kind of eccentric axial loading or something like that, the neutral axis is where the total stress value is 0. Okay. For example, for pure bending, neutral axis coincides with the centroidal axis. With the centroidal, CA means centroidal axis, okay? Centroidal axis of the cross section. Whereas for any kind of eccentric axial loading, okay? Eccentric axial loading means you will be having both bending stress as well as axial stress, okay? So during this type of loading, neutral axis can be either located inside the fibers, okay, or it can be outside the cross section, or it can be outside the cross section.
Sir, outside the cross section means it is not means there.
Yeah, it is not there. Actually, it is located in an imaginary position. Okay, that is the meaning of outside the cross section.
Okay, sir.
Yeah, maybe we will do some problems and then you will get to know. You will be clear with what I am saying. Okay. See, let us take this problem. I am having a beam. Okay, a cantilever beam, which is subjected to an eccentric axial load. This is the longitudinal axis, okay? And this I am naming it as E, okay? And this is subjected to an eccentric axial tensile load. And the value of E is D by 4, okay? So can you calculate what will be the axial stress?
P by PD.
Yes, this is a rectangular cross section I have noted, okay? This is a rectangular cross section. Maybe I can draw the cross section here, okay? This is B and this is D, okay? So the axial stress will be P by BD. And what will be the bending stress value? Or the maximum bending stress value, what will be the maximum bending stress value? It will be My by I, right? Which is equals to M by I into I by Y. And what is the term which I can represent I by Y as? Any idea?
Section
Z.
modulus.
Yes, section modulus Z, which is actually here I am denoting the section modulus by Z. Okay. So here, what is actually the definition of section modulus? I divided by Y. Here, what is the distance of Y?
D by 2, sir.
Yeah, d by 2, which means like the distance of the topmost fiber, okay, or the distance of the far away fiber from the centroidal axis, okay. That is the meaning of only when you are putting the value of y as the distance of the far away fiber from the neutral axis, then only it is termed as section modulus, okay. For example, if I am taking y distance to be here, then I can't say this as the section modulus of this entire cross section. Okay, only when I am taking the value of y as d by 2, then only I can term this as the section modulus. Okay?
Yes, sir.
Yeah. So sigma b max will be. Can anyone say what is the value of sigma b max?
3P by 2BD.
5p by 2bd, yes. So p into d by 4 is the moment, and bd cube by 12 will be the section modulus.
BD square by 6, sir.
Sorry, bd cube by 12 divided by d by 6. Yeah, so it will be uh, bd square by 6.
3P.
Yeah.
Sir, D by 6 or D by
D
2,
by
sir?
2.
Sorry. So what is
Eight
the
by
final value we are getting? 5PD, 5P divided by 2P, 2BD. Okay?
I am getting 3 by 2.
It is
three.
3p by 2bd.
Okay. Yeah, it is actually so we have actually calculated the bending stress value based on the cross. Okay, we are taking the bending stress value. We are actually calculating this separately. Okay, so it will be 3p divided by 2bd, and which will be this 3p divided by 2bd, which will be tensile for which and will be compressive for which fiber.
Top fiber compressor.
Yeah, it will be compressive for top fiber, whereas at the bottom fiber it will be tensile. Okay, so here it will be tensile. So I am writing it as positive, and here it will be compressive. Okay, so can you say what will be the value of the total stress at the bottom fiber and the value of the total stress at the top fiber? For bottom fiber, what will be the value of total stress?
5p by 2bd.
Yes. So it will be summation of axial stress plus the bending stress. And here both are tensile. So we are writing it as P by BD plus 3P divided by 2BD, which is equals to 5P divided by 2BD. And here it is tensile. Okay. And here what will be the value of the top fiber, total stress at the top fiber?
Minus P by 2BD.
Yes, minus P by 2BD, which means like sigma A minus of sigma B, because sigma B max is actually compressive, right? So when you are putting this, the value will be minus P by 2BD. Okay? So here we will draw the variation of the bending stress, okay, or the total stress from the top fiber and the bottom fiber. So in the top fiber, what is the value? It is like P by 2BD, huh? Which is compressive, right? So let us take this as the negative side and this as the positive side, okay? So this is the top surface, okay? And this is the total length, which is actually nothing but D, okay? And this is 5P by 2PD. 5P divided by 2BD. So here where you will get the neutral axis, you will get the neutral axis in between the cross section, okay? So this is the thing which I told you before, okay? So in some problems you will be having the neutral axis in between the cross section, whereas in some problems you will be getting the neutral axis outside the cross section, okay? So here you will be having the neutral axis in between the cross section. So this is the neutral axis. So how to find the position of the neutral axis?
Equating the area.
Yes, equating the area. Either you can like you can equate sigma A equals to sigma B max, okay, or sigma B at any cross section, which means like at the neutral axis the axial stress will be equal to the bending stress, Okay, so if you because at this point the tensile axial stress is balanced by this compressive bending stress. So due to this only you are getting the neutral axis at this position, which means the total stress value at this position is actually 0. So here what I will do is like, this is the d by 2, right? So I am taking this as the y value. Okay, so I want this y, I want to find out the value of y so that I can find out the location of the neutral axis. So this is very important for your gate question. Okay, so what will be the distance of this?
D by 2 minus y.
Yeah, d by 2 minus y. So from this, can I employ this? Either you can use this concept, okay, sigma A equals to sigma B at any cross section, or else you can use this concept, similar triangle concept. Okay, can you find can you use the similar triangle concept, and can you find the value of the y? Please do this
Yes.
sum, okay, and you come up the value of y. My phone is running out of charger, so I will plug in my charger. Okay, give me just 2 minutes. Okay. Have you solved the problem? Hello?
Solving, sir.
Yeah. So by using either similar triangle concept or by using the sigma A equal to sigma B, you can actually find out the value of the neutral axis, or the location, sorry, the location of the neutral axis, okay? So here I am employing the similar triangle concept.
D by 3, y is equal to.
Yes, that y is equals to d by 3. So let us solve the let us solve this by using the similar triangle concept. Okay. So here, what is the distance you are getting? This is p by 2bd divided by 5p divided by 2bd, which is equals to d by 2 minus y divided by d by 2 plus y. Correct? So from this, you will get y is equals to d by 3. So the neutral axis is located from the centroidal axis at a distance of d by 3. Okay, and it is towards the top fiber. Is it clear or not?
Yes, sir.
Or shall we work out one more problem on this, where the neutral axis lies outside the cross section? Okay.
Sir, in equating this bending stress, what stress bending stress we taking, sir?
Okay. See, for example, for equating the bending stress, you need to actually keep the value of y as y itself. Okay. For example, the axial stress will be P by BD, whereas the bending stress will be like P into E, which here E is actually D by 4, right? And for example, here you should not take the value of y as the section modulus, which is equals to d by 2. Okay, here you have to retain the y as y itself, divided by bd cube divided by 12. Okay, which means like my divided by I, which is equals to sigma b. And here, why I am doing like this? Because I am finding out the bending stress value at a distance of y, okay, from the central axis. This is the central axis, and at a distance of y, I am actually calculating the bending stress value. So I don't know what is the value of y. Okay, so but at this y, the stress value is actually equal to sigma a. So that is the concept of this. Okay, are you getting what I am saying?
Okay, sir.
Yeah.
Yes, sir.
See, for example, at this point, the negative bending stress value, okay, is equal in magnitude to the positive axial stress value. Okay, so here we are not worrying about the sign. We are actually calculating what is the, uh, for example, we know from this variation the neutral axis is located between the centroidal axis and the top fiber. Okay, on drawing the variation, we come to know this. So so we actually want to calculate the bending stress value at this. Okay, so for that we are writing my by I. So here I am retaining the y, this y value I need, which is this total stress is equal to the axial stress, which is equals to P by BD. So when I retain this y value and when I'm equating this with P by BD, I will get y is equals to D by 3. This is one method, and using similar triangle concept, the you can also find out the neutral axis, location of the neutral axis. Okay.
Okay, sir.
Yeah. So we will solve one more problem based on neutral axis. See, ultimately for pure bending, like we can say the neutral axis coincides with the central axis. Okay, since the bending stress is 0. Whereas for an eccentric axial loading, we can't say the neutral axis coincides with the central axis, because here we are defining for a eccentric axial load the neutral axis to be like where the total stress is 0. Okay, but for a pure bending, like we are actually having only bending stress. So we are saying like the neutral axis is actually coinciding with the central axis. Okay, so we are having a rectangular member like this. Okay, and this is the longitudinal axis. Okay, so here I am having an eccentric axial load P equals to 100 kilonewton. Okay, and this length is 10. So can you find out the axial stress separately, the bending stress separately, and then which side fiber you will take here? The top fiber, the bottom fiber, or the left fiber, or the right fiber?
Left and right.
Yes, left and right. Yeah. So can you calculate what is sigma A separately, sigma B max separately, and then can you calculate the sigma or the total stress at the left fiber as well as the total stress at the right fiber?
What is cross
Sir,
section?
cross section.
Yeah. The cross section is actually 50 and 100. Cross section is, this is actually 100, and when you see from the top, this is actually 100 and this is 50. Okay.
Sir, it is like a short column.
What? Hello?
Yes, sir. It is like a column.
Yes, it is like a column, yes. So I want you to find what is sigma A. What is the axial stress due to this point load? For example, how you can actually denote this by a pure axial load and a pure bending moment. Sorry. Okay, I'm replacing this same system, okay, by a pure axial load, which is equals to 100 kilonewton, and a bending moment, which is equals to 100 into 10, and it will act in this direction. Okay, for example, in this direction, maybe I can do this 100 kilonewton, and here it will be 100 into 10. Okay, and all the dimensions are in mm. This is mm, this is mm, 10 is mm here, and here also it is mm.
This representation means dynamically equivalent system.
Yes, this representation is not a dynamically equivalent system, it is a statically equivalent system. Okay, so here we are dealing only with statics, right?
Okay, sir.
Yeah. So can you say what is the value of the sigma axial stress alone?
Minus 0.02 kilonewton per mm square.
Okay, can you
200
say
MPa.
megapascal?
200 MPa.
20 megapascal.
Yeah, it will be 20 megapascal. So here maybe I will write the answer 20 megapascal. Okay, so sigma A equals to P divided by A. So P is actually what? I am writing everything in Newton per mm. That is the sign convention I am following, okay, throughout this subject. So 100 into 10 to the power of 3 divided by A is 100 into 50. So you will be getting sigma A as 20 megapascal. And what is the value of sigma B max, or the maximum bending stress value?
6 MPa.
Are you sure? Because I am having a different answer.
Which value, sir?
Huh?
Which value?
Maximum bending stress value.
24 MPa.
24 MPa, or like I'm having the value as 12 MPa. So
12 MPa.
12 MPa.
12 MPa.
Yes. So here we can write m divided by z. Since I'm actually calculating the maximum bending stress value, I'm writing it as m by z. Okay. So m is actually p into e, which is like here 100 into 10 to the power of 3 into 10. Okay, divided by bd square by 6. So it will be 50 into 100 square. Okay, divided by 6. So you will be getting it as 12 megapascals. So why we are actually taking 100 MPa means, I mean 100 square means this is the d value, because here I am actually getting the bending stress variation from left to right. Okay, so this will be the d. Okay, you should not take 50 as the d value. Getting what I am saying? See, you are actually having a cross section like this. Okay, this is 100 and this is 50, and you are actually having a bending moment which is actually making this to, for example, the right face actually gets contracted, whereas the left face actually gets elongated. So it will be negative here, okay, and this will be positive. So which d value I should use? For example, here you will be having some confusion, right? Whether I have to take 50 as d or 100 as d. So you can actually take that, come to a conclusion using about which axis the bending moment is actually acting. Okay. So since the bending moment is actually acting is in this direction, so you can actually find out the d value will be something. I mean, the bending moment is about this axis. Okay, about this axis. So getting what I'm saying, or should I have to repeat it?
We have chosen that axis because our movement was along that axis.
Yes, we have chosen this axis because our moment is along this direction, because this is the right fiber, right? When you are viewing from the top, this is the right fiber and this is the left fiber. Okay, and this cross section I have drawn when it is viewed from the top. For example, here if I draw means it will be like this, like a straight line. Okay.
Okay, sir.
Yeah. So can you say what will be the total stress at the left fiber? It will,
8.
yeah, it will be 8 megapascal. So it will be like sigma A plus sigma B max, which will be equal to, here sigma A is actually compressive, right? So I am writing it as minus 20. Okay. And what will be the value of sigma B? It is positive, so it is like 12. So it is minus 8 megapascal at the left fiber. Okay, and what is the total stress at the right fiber?
Minus 32.
Yes, it is minus 32. So sigma A against plus sigma B maximum. Okay, so here sigma A stays the same, whereas the sign of sigma B alone it will be minus 12. Okay, so it will be minus 32 megapascal. So why I am doing all these things? So ultimate aim is to find the location of the neutral axis, right? So only when you know the value of the total stress at the left and right fiber, then you can draw the stress variation across this cross section, and then you can find out the location of the neutral axis. Okay, so that is the total motivation behind this. Okay, so when I draw the variation, it will be something like this, stress variation. So both are negative, right? So maybe we can take this as positive and this as negative. So here it is minus 8 megapascal. Okay, and let us say this as the left fiber and this as the right fiber. Okay, and this is the right fiber, which is 32 megapascal. So can you find out, this is the total length 100. Okay, so here where the neutral axis is actually going to lie?
Left side.
Left side, yes. So if you are extending this, then you will get to know, like, this is the position of the neutral axis. Yeah. So again, by using similar triangles, can you find this? Let us take this as the distance x. And can you say what is the value of x?
100 by 3.
Yes, it is 100 by 3. So which can be written as 33.33 mm. Okay. So Here we can write it as like 32 divided by 100 plus x using similar triangle concept. Okay, by using similar triangle concept, 32 divided by this total length. Okay, 32 divided by this two triangles I am taking. Okay, this big triangle as well as this small one. 32 divided by 100 plus x is equals to this length is 8. 8 divided by x. So x you will be getting it as 100 by 3, which is nothing but 33.33 mm. Okay. So now it is clear, right, how you are actually finding the neutral axis.
Yes.
Okay. Yeah. So based on this, I will give some homework. Okay. I will be uploading the homework problems by tomorrow or day after tomorrow. Okay.
Sir, one thing I had to ask you.
Yes.
Sir, can we say that neutral axis is center of contraflexure?
No, yeah, that is a good question. Actually, why we can't say the neutral axis as the center of contraflexion means, or the point of contraflexion means, like we have defined the point of contraflexion as the where the at which point the bending moment changes sign. Okay, for example, in a given beam, okay, you can have the bending moment diagram to be like this. For example, like this, you can have the bending moment diagram, right?
Yes, sir.
These two are parabolas, okay? So here also the bending moment value is actually 0. But can you say this as the point of contraflexion? No. Because the point of contraflexion is defined as where the bending moment actually changes sign.
Changes sign, yes, sir.
Yes. So we can't say the neutral axis as the point of contraflexion. Okay?
Thank you, sir.
Yeah. So can we proceed to the next problem?
Yes, sir.
Yeah. So this time we'll be working out another different problem, okay? So here I am having again a rectangular. This is a different question, okay? Here I am having again a rectangular member, and this cross section is like 100 into 20, okay? This is 100 and this is 20, okay? And this is subjected to a pure bending moment like this. And what they have given is like after bending, the shape is like this. And they have given the angle, okay? This angle as 80 degree. So you have to determine maximum bending stress as well as bending moment. And the E value is 200 gigapascal. And the total length is 8 mm. So how to solve this problem? Anyone?
First, we find the maximum bending moment.
Radius of curvature.
Yes, actually we need to find the radius of curvature because like maximum bending moment we can't actually find, right? Because in order to find the maximum bending moment, either for example, if I have to find the maximum bending stress or the maximum bending moment, it is actually only this equation I know, or I can write this equation mi by y, or else I can write ey by r, ey max by r. This is another one equation. Okay, so here if I use this equation, both sigma b max and m both are unknown, so I can't use this equation. Okay, if I want to use this equation, then I need to know the value of r, radius of curvature. Okay, so as someone pointed out, like first we have to find out the radius of curvature. Is it clear what I said?
Yes, sir.
Yeah. So can you find out the radius of curvature? How to find the radius of curvature then?
R d theta is equal to 8.
Yes, r theta is equals to 8. Okay. For example, before bending, this is the neutral surface, right? And this is subjected to pure bending, okay? Sorry. So before bend, this is before bending, okay? And after bending also, you will be having the neutral surface like this. And what will be the length of this neutral surface? It will be 8 meters only. Because even after bending, the what is the definition of neutral surface is like the length of the neutral surface before bending and after bending remains the same, okay? So based on this, I am taking the overall arc length as L. Okay, here L is equals to 8 meters, and by this relation like L is equals to R into theta, you can actually find out the value of R. Okay, so in which unit I have to substitute this value of theta?
Radian.
Radians.
Yes, it should be in radians. So can you say what will be the value of R? 8 is equals to R into 80 degree into pi divided by 180. What is the value of
5.7
what?
5.73 meters.
Yes, 5.73 meters. So after knowing this radius of curvature, then you can actually find the value of sigma B max, okay, or the maximum bending stress value, which is equals to E into Y max divided by R. So what is the value of E?
200 into 10 cube.
Yeah, so actually the value of E should be 100, okay. So 100 into, I'm always substituting in megapascal, and the loading is in newtons as well as the dimension is in meters, okay. So into what will be the Y max value here?
10.
Yes, 10, and divided by 5.73 into 10 to the power of 3, because R is in meters, okay. So what is the value of bending stress you are getting?
174.
1.52.
Yes, 174.55 megapascal. Now from this, can you calculate the bending moment value?
Yes, sir.
Yes. So it will be by using this equation, sigma B max equals to m by z. So from this you can actually calculate m is equals to sigma B max is 174.55 into z. Z is bd square by 6. Okay. So here what is actually b and what is d?
B is 100, D is 20.
Yes. So don't get confused with this b and d, because when I study I used to get confused. Okay. So this is like bd square by 6. So it will be, what is the value of the bending moment?
Is it 1163 kilonewton meter?
1163 kilonewton or like a newton? Because
Kilonewton meter.
yeah, I think it should be newton meter, because I am having the answer as 1.163 kilonewton meter. Please check whether you are getting this answer. Is everyone getting this answer or a different answer? See, this is in megapascal, right? Megapascal means Newton per mm square. So I will be retaining this same value. Okay. B is in meter, mms. So I will substitute this as 100 alone. And 20 also it is in mm. So 20 square divided by 6. Then I think you will be
Yes,
getting
sir. Correct, sir.
this. Correct,
Ah,
right?
yes,
Then
sir.
Yeah,
Yes, sir.
yeah. Okay, so up to this it is clear, right? How we are proceeding about the neutral axis, location of the neutral axis, how we are actually calculating the bending stress, then how we are actually calculating the bending stress when radius of curvature is actually given, and then how we are actually locating the neutral axis, and then based on this concept also. For example, here we have written the maximum bending stress. Uh, for example, sigma b max is actually E y max divided by R, right? And what is the from the bending moment equation? What I can write E into y by R. So based on this, I can actually write sigma b max divided by sigma b, okay, which is equals to y max divided by y. Okay, for example, if I know the maximum bending stress value, okay, and for any location of y, I can actually find out the value of sigma b by using this relation, because y max is known by the cross section of the geometry. Okay, so easily I can find out the value of sigma b. Okay,
Yes,
getting
sir.
what I'm saying? Is it clear what I told now, or should I have to repeat?
E by R constant, sir.
Yes, E by R is constant. See, for a given cross section and a given material, E by R is constant. So sigma is directly proportional to Y. Okay. So, but I know always the maximum bending stress. Okay, I always know the maximum bending stress by putting the value of M by C. So easily I can get the maximum bending stress value as well as the Y max value from the given cross section. So these two are knowns. So if they ask in the question like at a given depth, okay, for example, at a given y, if they are asking what is the value of sigma b, then I can easily find out, right, by using this relation. So that is the thing I
Yes,
told
sir.
now. Okay,
Yes, sir.
yeah. So now I am proceeding to the different problem. Okay, so this is a new problem. Okay, for the cross section shown in figure, uh, determine the tensile force developed on the rectangular hatched area. Okay, for example, the cross section is like this. Okay, so this total depth is d, and here d is equals to 20 centimeters. Okay, and the total width is b, which is equals to 10 centimeters. And here I am having, this is the central axis. Okay, so here I am having this hatched region, okay, which is of 2 centimeters depth, and also here I am having another one hatched region like this. So can you say what determine the tensile force developed on the rectangular hatched region as well as the compressive force developed on the triangular hatched region? Okay, tensile force developed on rectangular hatched region. Okay, this is the question. Is my handwriting clear?
Yes.
Okay. Compressive force developed on the triangular hatched region, and you are having d is equals to 20 centimeter and bending moment equals to 20 kilonewton meter. Okay, and this is a sagging bending moment, which means like you are having compressive stresses on the bottom side. Okay, and tensile stress on the top side.
Clockwise, sir.
Yeah, I think someone is not muted.
Actually, I'm telling that mean clockwise, sir. In clockwise direction.
Okay, okay, okay. Yeah. Tensile stress on the triangular hatch region. Okay. So so it is like the bending stress variation is like this. Maybe I can draw this here. So can you find out the value of the maximum bending stress? Because you have been given the bending moment and you know the dimensions of the cross section, so you can actually calculate the maximum bending moment, right?
Sir, where the bending moment applied?
No, see, in the question it is given like a sagging bending moment, okay? Sagging bending moment, which means like you are having tensile, here you are having compressive, I mean the top fiber is subjected to a compressive stress and the bottom fiber is subjected to a tensile stress. Okay, and this can, we can say 1 and this is 2. Okay, or maybe I can rename this question itself 1 and this is 2. Now you are getting right here, fully you are getting tensile stress and here you are getting compressive stress. In the top region it is like compressive, in the bottom region it is like tensile. Now the question is clear.
Yes, sir.
Okay, so now can you say what is the tensile? First we can go for the rectangular area, then you can proceed for the triangular area. Okay, so how can we find the tensile force in the rectangular hatched region? Any idea? So the method is like this, okay? So whenever they ask the force, find the tensile force or find the shear force by giving cross-sectional area and they are actually giving the shear stress, you can actually always use this method, okay? The elemental force dF is equals to sigma into the elemental area dA, okay? And you can integrate it from the limit from here to here, okay, integrating it from y1 to y2. This is the basic concept for any stress, like even for example, maybe in the upcoming class we will see about the shear stress in beam. Okay, there also we will do some problem based on this same idea, okay, where the elemental force is equals to the stress at that elemental area multiplied by the total elemental area, okay, and you are integrating it from the lower limit to the upper limit so that you will be getting the total force, which is equals to, for example, if I have written elemental force, it should be like this. So the total force is nothing but integration of y1 to y2 df, which is equals to integration of y1 to y2 sigma dA. So how I can proceed this? See, first let us take the strip here, okay? Let us take an elemental area dy, okay? For example, based on this rectangular section I am drawing here, okay? This is the neutral axis, okay? And here we are actually taking an elemental area, which is of length dy or thickness dy multiplied by the strip, width of the strip, which is b. So what will be dA? It will be like b into dy, right?
Yes, sir.
Yeah. So dA will be equals to b into dy. And here I need to find out the value of stress. And this cross section, I mean this small strip, I am taking at a distance of y. So here if I know the sigma value, okay, And if I know the sigma value in terms of y, then I can easily find this. I mean, I can easily convert this equation in terms of y itself, and then I can integrate this equation in terms of y, and then I can find out the total force. So how I can do that? So for that, I need to find out the stress at this uh, fiber, which is at a distance of
M1
y. Yeah. Yeah. Someone was about to say something, right?
So sigma is my by I.
Did you say? I couldn't hear you properly.
Sigma is my by I.
Okay, my by a. Okay, that is one thing. For example, using that also you can't actually find. For example, you can actually find out the maximum value of bending stress. Okay, and based on that you can actually use this equation, right? And you can actually convert this sigma in terms of y.
Yes, sir.
Yeah. So what will be the maximum value of bending stress for this given question?
Is it 30 MPa?
Yes, it is 30 MPa. So here I am writing, okay, sigma b max equals to m by z, okay, which is equals to 20 kilonewtons, right? So 20 into Newton I am writing, and kilonewton per meter also, kilonewton meter also. So 20 into 10 power 6 divided by z is actually what? BD square by 6. So it is in centimeters, so I have to convert this to meter, mm, okay? So 200 square divided by 6. Okay, so 6 I am taking it to the numerator. So you will be getting 30 megapascal. Okay, so from this, what value of y should I put, and what would be the value of y max? For example, sigma is equals to sigma b max. Okay, sigma b max is actually 30. Okay, into y. What is the value of y here? Here at this point I need, right? At this point I need the sigma value. Okay, and then I can write it the integration from 8 to 10. For example, this total length is 20 centimeter. Okay, so half of this is 10 centimeter, and here they have given for this 2 centimeter alone I have to find out the tensile force. So it will be from 8 to 10. Okay, so what will be the y value? It will be 8. And what will be the y max value? It will be 10. Okay, so this will turn out to be 24 megapascal. But here the f value is actually sigma into d into a. Here sigma is actually changing from fiber to fiber. So I have to write this whole sigma in terms of y alone. Not I should not substitute in terms of y. This sigma is actually at this fiber alone. Okay, and this is a constant value which is equals to 24 megapascal. Okay, and this is actually varying all through this hatched area. Okay, so what I have to write? I have to write it from 8 to 10. I am actually, or from 80 to 100 in terms of I am actually substituting. Okay, and I will be writing it as sigma b max. Okay, into y divided by, sorry, I'm actually writing it not as writing. Okay, so f is equals to integration of 80 to 100. Okay, sigma b max. Instead of sigma, I am writing sigma b max into y by y max. Okay, into y by y max. And what will be the value of dA? It will be like b into dy. Correct or not?
Yes, sir.
Yeah.
100 into 2.
Yes. So it will be like sigma b max is constant, which is equals to 30, and y max is actually 100. Okay. So I am taking these two outside. So it will be like 80 to 100. B also is constant right here. Width of this strip is constant, which is equals to 100. Okay. So
Yes, sir.
100 into y into dy. So can you solve this and can you find out what is the value of the total tensile force in the rectangular hatched area?
540 kilonewton.
540?
Kilonewton.
Okay. So if anyone is getting different answer, I'm actually having the answer as 54 kilonewton. So
हाँ सर 54 है सर.
yeah, it is 54 kilonewton, right?
Yes, sir.
Okay.
Sir,
Yes. Yes, someone was asking some doubt. No?
no, sir.
Okay. So shall I proceed then? This is clear, right? How we are actually proceeding, or how we are actually solving this problem. Okay.
Yes, sir.
Yeah. So next we will move to this second question. Like, what is the compressive force developed on the triangular hatched region? Okay. Same method we are actually going to follow. Only thing is like here the width of this is actually changing with y. Okay. Here the width of this strip is actually constant, right? Here width of this strip is actually changing with respect to y. So how to solve this?
Expressing b as a function of y,
Yes.
then find the
So
d,
how you will do that? Expressing b as a function of y.
which will be
For example, I am having like this. Okay, and I want this b strip, which is actually a function of y.
here b equal to y, sir.
B equal to y. How you are getting that b equal to y?
ये लाइन की इक्वेशन सर.
Which equation?
इक्वेशन ऑफ द लाइन.
Okay, equation of the line. Yes, that also you can use, or you can also use similar triangle. Okay, so here I am using similar triangle concept, and 100 by 100 equals to, and here I am taking this as a small strip. Okay, of length. For example, this is y. Okay, and this is dy. Okay, so what will be? This will be b strip, and this will be y plus dy. And since dy is actually a very small value, we can actually ignore dy. Okay, so you will be getting b strip as approximately equal to y.
Is force 100 kilonewton.
Yes, the first value is 100 kilonewton. Yeah, correct. So the total force will be, here I am denoting the total force of this rectangular hatched region as region 2. Okay, or the question 2. So it will be like same 30 by 100. Okay, here what will be the limit of integration?
0 to 100.
Yes, it will be 0 to 100. And what is b strip into dy, right? So b strip into y into dy. Actually here some y will be remaining and b into dy, like that we have seen the earlier thing, right? Here this one, y b dy. Okay, so here y remains the same. So instead of b strip, since b is here changing, I am writing b strip in terms of y. Okay, so here I will be getting 30 by 100, integration of 0 to 100, y into dy. So on integration, you will be getting the value as 100 kilonewton. So is this problem clear to everyone? Or should I have to again explain this problem? Yes?
A similar triangle rule.
Similar triangle I have to explain again. See, actually, for here, what is see here? I want the expression of B strip since B strip is actually varying with respect to Y. Okay, so I need to express B strip or the width of this strip in terms of Y. Okay, so what I'm doing is like I'm taking an elemental area which is equals to B strip into dy. Okay, at a distance of y from the neutral axis. This is the neutral axis. Okay, so based on this similar triangle concept, I can write 100. This 100 divided by this length 100, which is equals to this triangle I am taking. Okay, b strip divided by y, which is like approximately it is actually equal to y. Okay, so we are ultimately getting b strip is approximately equal to y. So I can substitute the value of b strip as y, and then on integrating I will be getting 100 kilonewton.
Okay, sir.
Yeah.
Sir,
Yes.
sir, force where apply at cross section can you show in diagram?
Force. So
Yes, sir.
you want me to show the force in this cross section?
Yes, sir.
Okay. See here it is actually compressive stress, right? In the top region it is actually compressive stress, right? So I will
Yes.
be getting compressive force only. Okay. Here I will be getting compressive force. But this compressive force you will be seeing from the right hand side when you are having this cross section as the right cross section. Okay, for example, if I am taking this cross section 20 cross 100 as the right hand side cross section. For example, I am having a bar like this, and this is the cross section. I mean, this is the cross section of this. Okay, then from right side here you can see the compressive stress like this, or the compressive force like this. Okay.
Okay.
Okay. So up to this, it is clear. Yeah. So here is a different question. So with this question, we will wind up the topic of bending stress, and in the next class, we will see the shear stress in beams topic, and then we will proceed to the deflection of beams. Okay. So this is the last problem for today's class. Okay. So find the maximum flexural stress developed in a steel wire of 2 in diameter if it is coiled over a drum 0.5 meter in radius. Okay. What is the bending? And you have to also find out what is the bending moment to which the wire is subjected to. And you can take the value of E as 20 gigapascal. So can anyone try and come up with the solution? So first, what is actually given in the question? You are actually having a drum, okay, which is of radius 0.5 meters, okay, and over this you are actually coiling a steel wire. Okay, this steel wire is of diameter 2 meter. Okay, this steel wire is of diameter 2 meter. So how to solve this question? How to find the maximum flexural stress? Or how to find out the bending moment value? Any idea? Or which equation you will actually use to solve this problem?
सर बेंडिंग वाली क्वेश्चन यूज करेंगे ई बाई रो वाला जो फॉर्मूला है
Yes,
उसके थ्रू.
yes. So bending is actually given by m by I equals to sigma by y equals to E by R. Okay. So while using this, you have to use sigma is equals to Ey by R. Okay. So sigma equals to E into Y by R. So what is the value of R here?
R1
1.
sorry 0.5 meter.
Yes. See, This steel wire is actually coiled over this drum, right? So you will be having neutral surface like this. Okay. So if you take the radius of curvature of this neutral surface, it will be approximately 0.5. Okay. So you will substitute the value of R as 0.5 into 10 to the power of 3 mm. Okay. And the value of E will be 20 into mega 10 to the power of 3 megapascal. And what will be the value of Y?
10 to the power minus 3.
10 to the power of minus 3
नहीं 10 to the power
minus 3 meter, yeah, 10 to the power of minus 3 meter, and in mm it will be 1 mm. Okay.
okay sir.
Yeah.
400 megapascal.
Yes. Good. 400 megapascal. And what will be the value of the bending moment? You can again use this formula, right? M by I equals to E by R. So M will be equals to E I by R, which is equals to 20 into 10 to the power of 3. What will be the value of I? What is the cross section here?
uh, value of
I.
I तो पाई है ना.
Circular cross section, yes. See, since the circular wire is actually bent over this drum, okay, so it will be a circular cross section. And what will be the moment of inertia? The moment of inertia of the circular cross section?
Pi by
4
4 into the power 4.
Yeah, pi by 64 into d to the power of 4.
4.
So
Yeah.
pi by 64 into d is here 2 mm, 2 to the power of 4 divided by r is 0.5 into 10 to the power of 3. And what is the value of m?
314.2.
314? Yeah, 314.2 Newton.
mm.
Yes, Newton mm. So up to this it is clear, right? What and all we have seen in today's class. We have seen only the bending stress in beam in today's class. Okay. And if they are asking, for example, in shear force diagram also they can ask the bending what will be the bending stress at any cross section. So or during that problem, like you have to find out what is the bending moment at any particular cross section. Okay, and then you have to use this m by c formula to get the bending stress value. Okay, for example, if there if my bending variation is like this, okay, and I know the equation of this bending moment variation, okay, and they are asking what will be the value of what is the value of bending stress at x is equals to say 1.5 meter from the left side. Okay, so at that time what you will do, you will actually calculate the bending moment, okay, and you will divide it by the section modulus value to find out the bending stress. Okay, this is the another variant in bending stress problems. Okay, so I'm here stopping at this moment. Okay, so let us meet in tomorrow's, I mean the next week's class. Okay, yeah.
So, so I had doubt on the last session. So you have discussed a problem on the problem about a beam and a extruding section. Um, in that section, you have find the concentrating moment at a point.
Okay,
So
one
how
minute.
did you find that concentrating moment?
Okay, 1 minute.
There is
Uh, 1 minute. I will take that PPT.
uh,
December 19, right? Yeah. In this, which problem you are referring to?
there was a first problem that you have discussed before the uniform distributed load.
Okay. Yes. 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 So you are mentioning about this problem.
Yes, sir. So you have find that constant moment at that point B.
Yes.
How did you find that constant moment? Did you transfer the force from P to B?
Yes, I have transferred this force P at E from E to B. Okay, for
Sir,
example, huh?
okay, sir. So when you are discussing this type of problems before, you said that actually we need to take the reverse moment at when we remove some section from the main body.
Yes, yes, yes. See, actually, here what is happening is like, for example, when I'm considering this section BD alone, okay. For example, at section, for example, when we are considering this DE, okay. So here you are
Okay,
applying
sir.
force like this, right? So here, in order to ensure this equilibrium of this member DE, I have to apply a force P like this, okay. But when I'm considering this BD member, again I have to reverse this direction, okay. So again I will be having a P force like this, and this is D, okay. So due to this, what will be the moment direction at point B? It will be P into L by 3, right?
Yes, sir.
So my direction is correct, right? See, here I have, in order to ensure the equilibrium of this section DE, I have taken the opposite direction. Okay. For example, P is acting in this direction. So to ensure the equilibrium of member DE, I have taken the opposite direction. But when I am coming to member BD, again I am reversing this direction as I have told earlier. Okay. So I am reversing this direction and then I am finding out the bending moment at point B.
So we will be removing that dB also, isn't it? So it will be reversing, isn't it?
No,
When
no,
we
no,
consider
no.
the AC.
No, that we should not do because at this moment this is like an external force acting like this.
So AC and BD member will be considered as single one.
Yes, yes.
Sir, is there any reason we take like that? We remove the first section, first member from the main body. We didn't remove the DB.
No, actually, see, for example, before problems which you have worked out, right? For example, here, if you have seen like this problems we have worked out like this, right? Here B is there, A is there, C is there, D is there. So here we are actually calculating BD sections like this. Okay. So for example, if I'm having maybe a force like this P. Okay. So what I have done is like I have taken, for example, let this be L. Okay. So I have introduced a moment like this only, P into L. Okay, this same moment I am replacing it here by in the opposite direction.
Okay, sir.
So, for example, if I am doing in a similar procedure, okay, so then what I have to do, I have to introduce, for example, I am drawing it here, okay. This is D, okay. This is my force P. This is my point B, okay. So, due to this P into L by 3, I will be having a moment like this, right or not?
Yes, sir.
Yeah. So when I'm considering this whole member ABC, then I'm inverting to this direction P into L by 3. Now it is clear, right?
Yes, sir.
Okay.
Okay, sir.
Yeah.
So either we can do this also by transferring the force from P to B also.
Yes. Either I can see since this is somewhat trivial, so I have actually used this directly. But you can also proceed as I told you earlier, like step by step. Like DE, I can take I mean as a separate individual member, and DB I can take as a separate individual member, and then ABC as a separate individual member. Okay.
Okay, sir. So the same procedure is happening there also.
Yes, here also it is applicable. For example, here I have told you, right? For example, P is acting like this. So here I am taking DB as a individual member. So due to this shear load P, I will be having a moment reaction here. which is in this direction PL by 3. Then when I'm considering ABC, I'm introducing PL by 3 in the opposite direction.
Okay, sir.
Yeah.
Hello, sir.
Yes.
In today's question of finding tensile force and compressive force on a triangular and hatch area,
Yes.
we can't go, we can't use the method that finding mean stress and then multiplying the stress by area.
No, there is no. I think there is no actually, there is a concept called average stress like that. Okay, but I think it won't be possible. Maybe if, how you will actually calculate the average stress here?
Suppose at a neutral axis zero stress and at extreme
Hmm.
30 MPa. So 50 MPa as average.
No, no, no. Here, since the bending stress is actually varying, you can't actually. To my knowledge, I don't think we can actually calculate average bending stress, something like that. Okay, either we can go for
But
maximum bending stress value, or what to say, zero, the stress value at the neutral axis will be zero. Okay, but we won't be calculating average bending stress value. I actually I haven't read like that. Whereas you can actually find out the average shear stress value at a cross section. Okay, whereas you can't actually find out average bending stress at a cross section, to my knowledge. Okay.
okay, means
Hmm.
bending stress even if linearly varying then also.
Yes, because since it's varying, right? So I don't think we can come up with some kind of average bending stress value. Since, for example, here we can see this as the variation. Okay, this is 30 mega. This is pure bending case. Okay, let's imagine this has 30 megapascal tensile and this has 30 megapascal compressive. So can you say how we can actually calculate the average bending stress here for this cross section?
No, for this cross section, I think it is not possible. Means
Yes.
it is going zero.
Yeah. So for that only, like in the before problem also we have taken, like, since the bending stress is varying like this. Okay, from the neutral axis. This is the neutral axis. Okay, and the bending stress is varying from the neutral axis. So we are actually going for integration. If possible, maybe what you can do, you can actually what to say, for this cross section alone, maybe you can actually find out the average bending stress, and then you can find out the uh, uh, tensile or compressive force, which gives the same effect. The effect should not change. Okay, when you are substituting in terms of average bending stress, the effect should not change. Here, what I mean by effect is like the loading conditions or the total force conditions, that should not change. Okay.
Hello, sir.
Yes. Whereas to my knowledge, I haven't come across average bending stress. Whereas I came across the term average shear stress. Okay. Yes.
Okay, means that upper half portion also means not possible
I think so. I think so.
because means it is not giving the answer that we have calculated by our method.
Mm, yes. Maybe I have to think about it after this class.
Okay, sir. Thank you.
Yeah.
Sir, can you share the recording of these sessions
Yes.
and
Yes.
afterward?
Yeah. In the Google Drive, I will share it. Okay.
Okay, sir. Thank you, sir.
Yeah.
So next class we are starting with.
Next class, I am starting with shear stress in beams. Then I will go to deflection of beams. Okay.
Sure. Thank you.
Sir?
Today's class was started at 7 or late?
7:10 actually I started.
Because I was not able to log in into this gate portal.
Okay. Actually, I started at 7:10.
Okay.
Yeah, I will upload the videos in the Google Drive. Okay. So is it fine?
Thank you, sir.
Thank you.
Sir, your notes is available?
Yeah, homework I will upload by tomorrow or day after tomorrow. Okay.
Okay, sir.
Yeah.
So thank you.
Thank you.